Hello, here's Malban again, and how else could it be? I'm going to talk about Vide. Today I would like to show you what I've been up to lately, what I've done to Vide, and what are my plans to do next. Actually, I've been up to quite a lot of different things, but today I would like to show you what I've been up to in the respect of graphical output. As you might know, Vide is a Java program, and I used to do all graphic output with the usual Java routines using Swing, and that is obviously quite slow sometimes, so I thought a lot about what to change. Some month or a year ago I tried OpenGL with a library, but I couldn't get used to it, and I thought it was it's not my way of, it was not my way of programming. After that, I had enough of that, and I thought I would never look at it again, since Vide uh, should always be an integrated development environment, and it's not so much about uh, emulating and actually playing the game. Well, nonetheless, the last couple of weeks I considered again, and I started to implement a new graphical system using OpenGL. Another library, Joggle, or I don't know how you pronounce it exactly in English, is the library of choice at the moment, and I'm going to present you what I've done with it so far. This video is going to be quite technical, so if you're not interested in how Vide actually works, only interested in backtracks, or only interested in development vector claims, this video is probably not for you. But if you are generally interested in Vide, you might as well look at it. So what I'm going to do is open the actual emulator, Vexy. This is it. In parallel, I open the starter view, and I'm also going to add the configuration window, and here you can see all the changes that I've done, and I will show you how you might use the configuration yourself to maybe get an even better output than I did. The gist of the new implementation is that it is very configurable, and that you can, change the output very much to your likings. At least I hope so. So I will just start by loading a game. This is the old Mindstorm, and the graphics that you see right now are the old graphics. As I don't really like throwing good code away, the old graphics implementation is still available for anyone who, for whatever reason, might not have access to OpenGL. So this is the old graphics, and there's a new tab in the configuration. It's called Display. Some items from the first emulator tab were put onto the display because, I think they fitted quite a bit better there. This is the old graphics, as I told you, and I'm going to switch to the new. You can switch between all graphics on the fly, and you will see the difference immediately. This one is a most important checkbox for the moment. It's called Joggle, and with it we enable joggle output. This is what we do now. What you see now, it's not really good because it's a configuration taken from the old graphics and applied to the joggle graphics. This is not really, sensible. For the show, I've prepared some configurations, and I will load them now. Configurations, as always, can be loaded with a combo box above here, and I configured 4 items for now. line 1 clean, line 2 clean. I'll show you the difference later. For now I'm going to demonstrate with line 1. This is the output for line 1 I configured at the moment. Line 1 obviously means that the line width is 1. As before, you can toggle on or off overlays. It's the same button, but it's moved to this tab. You can do that here. For the moment, I will switch them off so I can show you a little bit more. Line width can also be determined as before with this slider over here, and you also have the same old persistence slider. This is quite few persistence, and I can enable it. This is nearly full persistence, so everything, nothing will be deleted, and well, everything else is something in between. Depends on what you like, actually. So I'll leave it somewhere here. You can below in the joggle configuration there are shaders. I will come to that later. For now I switched all shaders off. You have a brightness control over the vectors. It is a much finer brightness control than before. I will leave it somewhere here. Anti-aliasing, however you pronounce that in English. You can switch that on and off. You can see the effects immediately. Suppress double draw on lines is doing nothing anymore. I will throw it away. If you enable joggle, you have two anti-aliasing algorithms. It's a hardware algorithm of most graphics cards. This is MSAA. Multi-sample anti-aliasing, you can switch that on and off. If it's switched off, it's probably a software implemented anti-aliasing by your graphics card or by your driver, and MSAA is most probably a hardware implementation. It functions with multi-sample, and these are the number of samples you can configure depending on what your graphic card supports. 8 samples is quite good. 2 is a little bit, well, not so good, and so on. So this is anti-aliasing. Usually MSAA is the best thing you can switch on. Then you can configure a couple of shaders. I'll load clean again, switch that off. There are two shaders which are configured separately and are also executed separately. Actually, there are a couple of more shaders. The persistence is realized with the shader, overlay is realized with the shader, spill and glow is realized with the shader, so there was quite a bit of shader programming done. Anyway, the spill shader, you probably have not heard of that before because I invented it. The thing behind spill, or what I call spill, is that in raster graphics you usually have, if it's an 8-bit raster graphic, you have a brightness of 0 to 127 or 256. In the case of the Vectrex is from 0 to 127. Where 0 is total darkness and 127 is full brightness. So you might think that could be easily emulated, but the thing with the Vectrex is that if two lines join at some location, the brightness is doubled, or at least the feeling that the brightness is doubled. I don't know if it's really doubled or quadrupled or only half added or whatever. Anyway, the brightness is actually as anything with a Vectrex analog. So it even a brightness of 127 is not always the same, as you will see later. So if two vectors are joined, or a dot is drawn for a couple of hundred cycles, the brightness increases steadily. So even brightness of 127, if kept at one location, is after 1 second a brightness of, I don't know, 10,000 or something like that. So you cannot really put a finger on your actual brightness. The spill shader I implemented is supposed to support that at, well, I'm going to explain. The thought behind that is that well, I'm trying to explain it using the overlay of Mindstorm. So I switch it on, and if you look at these 9 squares, think of the middle square as a point, in quotation marks, of the vectrex. If the line goes from here to here with a brightness of 127, this point does have a brightness of 127. If a second line comes from here to here, joins in this point, you can think of the brightness at that location as of 200 or don't know, 256 or something like that. And the spill shader now has a threshold that you can determine here, and if the brightness on a pixel is brighter than the threshold, then the brightness of the pixel is distributed to all neighboring pixels. So say if the threshold of that imaginary pixel is 127 and actually it is 256, then 15% of the brightness that is higher than the threshold is distributed to the squares. 15% to that, 15 to that, 15 to that, 15 to that, and to the diagonal squares each 10%. It's in total 100%. 100% of the threshold overflow is distributed to the neighboring pixels. This shader can be called a number of passes, so that the pixels are distributed further and further as the brightness of one point or one pixel is very much higher than the threshold. It's I don't know if I explained that very well, but well, I tried. So what you can do is you can play with that shader. I usually say the threshold is 0, so every brightness is distributed, but you can actually use thresholds. The initial divisor, in this case I've put 3, since the graphic card is only an 8-bit graphics card, or I configured that the OpenGL frame buffer is 8-bit. The maximum value a pixel can have is 255. To actually allow spilling, I divide that 8-bit value by some divisor, and everything that is above using a divisor of 3 allows us to, well, have an overflow of 3 times the maximum. That's how you can look at it. What you see here now is the original output of the first render engine, you might call it, and this output is taken as input for the spill shader. So at the moment the spill shader is switched off. I can switch it on and you can see what these values actually do with it. If I switch it on, then all points are distributed to the neighborhood. It's distributed. The more passes I configure. Right now it's 3 passes. If I configure, 10 passes, then the actual brightness is further distributed at the cost that the overall image is much darker. So it's logical if you think about it. Spill path of 1 is 1 distribution, 2, and so on. So you can see it's sort of a blur, but not a traditional blur. The output of the threshold of the spill is actually again multiplied by the factor I supply here. If I have a factor of 1, it's very dark because everything is spilled to the surroundings. To get a value which is actually useful again, we have to multiply it again, also to compensate the initial divisor. Otherwise, the graphics will always be very, very dark. So if you multiply it by 6, it's a little bit brighter than the original, or the data will be brighter the higher the factor is. So this is a really blurry image. What we actually want to do with the spill is configure some kind of spill and glow. What we can do now is add the base. The base is actually this original output. We can add the base, and now it looks already glowy. What I added here is the original base, this here. And if I switch this on, I think it's named incorrectly. If I switch this on, the factored phase, the initial divisor is applied to the base, and it's then added. That it shows it's a little bit darker. By playing with these values, you can actually design cool effects. You can see if these two here meet already, the glow is intensified where these vectors actually meet. So this is the first shader that influenced the output, and I've got a second shader. There's a classical blur shader, a Gaussian blur shader that can also be configured. As input, this glow shader either takes the original if the spill shader is switched off, or the output of the spill shader is goes to the glow shader if it's enabled. So if we enable it now, the output of the spill is put into the glow shader and again transformed. The glow shader or the Gaussian shader also has different parameters, which are, might not be normal, or how can I say it? To demonstrate, I switch off the spill shader and only use the glow shader. If both are switched off, this is the original, and I switch on the glow shader, and here you have different configuration items. The passes is classic. You can look that up in the wiki what passes do. It's actually implemented as described in the internet with a vertical and a horizontal part, and the Gauss sigma value can be input here, the Gauss radius, and a threshold that is new. This is a threshold of actual brightness data that the shader should transform. So you can say only brightness values higher than 0.8 or something like that should be transformed, should be used. most of the time I leave that at 0, but so all data is processed, but you can play with that. Then there are two additional configurations. You can configure that the output of the blur passes are additive or, well, non-additive. You can see the difference. I switch additive off and configure a Gauss sigma as 0.5, then you might actually see something. Blur passes, well, somehow my keyboard is acting weirdly at the moment. You can see non-additive blur. You usually have to do many passes to actually see some good effect. The actual radios can be quite small. One is probably enough if you do that many passes. Or if I switch to additive blur, you will see full brightness. This is the difference. Here you usually do less passes, but take a high sigma value, and and here you can take a bigger radius, and at some point there actually is some blur that one can use. So here you see already a usable glow. The add base is the same add base as before, so you can add the original input data to the output data. This is what this does. It's a little bit brighter, so you can see also here this is already a glow shader. These two combined are now very glowy. You actually have to configure it yourself if you want a huge glow, a small glow, if you want to use spill or glow or both. The two examples I did implement both, and I like it. It's a good kind of glow in my opinion, but well, you have to see that yourself. Then there are some additional things you can configure. Actually, more or less you could do that before, but I think I never put it into the configuration tab. It's actually the case that the output of the vectrex of brightness depends also on the speed of the vector beam. So if you have a line that is drawn with a brightness of 127 and the line is only 1 centimeter long, or has a low strength, a strength of, I don't know, 10 perhaps or something like that, then the brightness is higher than a vector of the same brightness which is 10 centimeters long or something like that. And this can also be configured. Vector speed maximal reduce factor. This is the way that the speed influences the brightness of the vectors. So if this is extreme. Now the longer the vector, the less bright it gets. So actually speed reduce of 1 is the maximum reduce, and 0 is no reduction. So all vectors are actually the same. Wait, one moment. The same brightness. So here you see there are small vectors here and a large vector here, and it's more or less the same brightness. If I put a 0.9 here, then you see these long vectors are much less bright than these vectors over here. This is the effect you see here is a bit too much, so I configure it at some 0.3 or something like that. You can discern a difference as you can on the real vectors, but it's not disturbing. Then there's a dot dwell divisor. This is also what I mentioned before. On the vectrex, dots especially can be drawn using something called dot dwell time. The vector beam does not move and is kept at the same position for a number of cycles. And actually, internally, Vide collects cycle information. If a vector beam is not moving and switched on, per cycle, I think a value of 4. Don't ask me why I chose 4. It is that now. I add a value of 4, and that value is added to the brightness. And this is actually a divisor with that the brightness of the dot is again divided, and the result is put into the graphics engine and can be used via the spill or glow factor. So these things over here are actual dots, and you can see an effect if I change the value for these dots in Mindstorm. The smaller the divisor, the brighter the dots get. You see I don't know, I hope you saw the effect. I'll take 1 as a divisor there. Well, at some stage it doesn't make much difference, but if I take a divisor of 90 or something like that, then the dots are really are again dots and are not glowing. So I usually take a value between 20 and 40, and that is quite okay in my opinion. So these are all the shader brightness adjustment thingies that you can do. One last thing I implemented has to do with overlays. The overlays, as seen before, can be loaded with this button over here. And what you already see here is an adjusted overlay. There's a box here with overlay adjustment configurations. If I switch that off, this is the original overlay that is loaded from disk. As you might discern, there are areas which are more or less transparent, and there are areas that are not transparent or opaque. So, in my opinion, it is not very easy to do really good overlays in one image. The image loaded is a PNG image. It has alpha values, but in my opinion it does not look so perfect. So I have chosen some values with that you can adjust the overlay. You can turn on the adjustment with, well, adjust overlay. And there are some values. As I said before, the overlays have transparent areas, and the areas are usually not totally transparent, but have some transparency, some alpha value. The alpha value usually goes from 0, which is totally transparent, to 255, which is totally opaque, and something in between, well, shines through. To adjust the overlay, I internally have to determine somehow which areas of the overlay are actually transparent and which are opaque. You might say that is very easy, just look at the alpha value. It's not that easy, because as you see here, the grid actually is opaque, and something behind the grid or in between the grid is transparent. And the image, as you I have guessed, can be sized or resized. And what GL or any scaler does is scale all pixels, and the result can be that there are subpixel information. So the transparency value of this horizontal line is probably not 100% opaque anymore, but a little bit transparent, because the line actually is mixed with the surrounding areas. So a little bit of opaqueness is, while scaling is done, is put into this line. I don't know if you're really that interested, but you might look at subpixel information in the internet, perhaps that describes it better. Anyway, the gist of the problem is that I somehow have to determine what's transparent and what's not, and it's not just as easy to look at the alpha values, so I have to use a threshold. Anything, if I put 1 in, or an impossible 1.1 in here, then everything, to say that otherwise, everything below a value I give as threshold here is taken as transparent. The value actually goes from 0, which well, is equal to 0, to 1.0. It's a float value in OpenGL language, and the 1.0 actually is 255 in, well, normal 8-bit values. So the 1.1 here is actually an impossible value that cannot be achieved in any way, but taking anything above 1 tells the image everything is transparent. If I put a 0 in here, then I've got the original overlay as I would have if adjustment was not done in any way. So for this example, there's a 0.8 I take as adjustment, as a threshold, and everything that is adjusted uses only this thus got alpha, or the transparent information. With the overlay alpha adjustment, I tell the engine to actually reduce the alpha value by the factor given. So if I put a 1 in here, I do not reduce the alpha value at all. But for my taste, the transparent areas are much too bright. And I like the transparent areas to actually be, well, blacker. If you take a Vectrex image, and the less the factor is, the blacker, or the more transparent the actual transparent areas are. So if I take a value of 0.5 here, then you see all the transparent areas are quite a bit darker. If I put a 0 in here, then the transparent areas are actually black. The Vectrex image. Well, I think I took 0.4, something like that. It's quite dark already, but it's not totally black. One should see the transparent areas a tiny little bit. So, and the last adjustment value is is the color adjusted for the actual Vectrex beam, if I may call it that. So everything that is drawn onto the Vectrex area. The input data to use is what is the alpha value of the overlay, what is the actual color of the transparent area, and what is the brightness of the vector, or of the Vectrex beam data, or whatever you want to call it. And the alpha value, the original alpha value, is adjusted with the brightness of the actual Vectrex data multiplied with that factor. So, short explanation, the higher this factor is, the brighter the vectors are printed in the color of the transparent area. So if I put a 0 in here, then the original brightness that would shine through the original overlay would appear. No, I got it wrong myself. This is actually, if I put a 0 in here, then the original brightness of the vector is used and no information of the alpha of the transparent area. If I put a 1 in here, the higher the value I take here is, the more the transparent area is influenced by the brightness of the actual vector. This is complicated to explain. Anyway, you can even put 10 in here, then it explodes, but I usually take, I don't know, 0.5 I wanted to take, then the shine through is quite bright. You can configure it brighter, but anything brighter, I think, than 0.5 can actually be also configured via the glow or the spill shaders. Well, anyway, that way you can adjust the overlay or the brightness of the data coming through the overlay. So this example in here is my clean line 1 actually, and I've also configured line 2. This is again a little bit brighter, and the lines are actually, well, 1 pixel wider. So overall it's much brighter again. So last but not least, I might show you why I did all this, because the original non-joggle data probably could have also be adjusted. But let's look at the speed of the thing. For now, the speed limit of 100% is switched on. The brightness is not all that bright. I might adjust the brightness. Well, brightness here. Do glow, and here you can adjust the brightness. Now it's, well, somewhere at the stage of the brightness of the joggle implementation. Now I look at the speed. I switch off the speed limit, and you can see, well, right now it bounces between 95% and 100% speed. If I switch to joggle, I use the joggle data and switch speed off again. Then you can see we are at the speed of something about 250-260%. The new graphics engine is quite a lot faster. It's I think most of the time about 3 times faster than the old stuff. And one of the bad things of Vide always was that it was quite slow. This is, with this implementation, not true anymore, I think. Well, I hope it was at least a little bit interesting for you. Anyway, this was my show for today. Goodbye.